Thank you very much. I will turn the video off right now for the duration of the talk, and I'll turn it back on if there are some questions. And thank you for the invitation and the kind introduction. And Levi, be ready, because I have now a little bit more time and I will start bugging you again.
All right, no problem. Looking forward to it. Yeah, we should pick it back up.
Yeah, no problem. It will happen sooner than later.
Yeah,
okay, so
sounds like a plan.
No problem. I'll talk about my maybe small perspective on scientific machine learning and how this can help with a radiation transport problem. So we are at the conclusion of a 4-year grant that I led. I'll tell you a little bit more about it during the talk. So I've listed also all of my collaborators, research associates, and grad students who helped here. You see this color coded. So the maroon is Texas A&M, and the burnt orange is University of Texas at Austin, also known as TU around here. So when you think of, okay, what is scientific machine learning? Well, what tools do you really will you be using when you do scientific machine learning? Well, you can find, for example, on stochasticlifestyle.com, and I think we had one of the guys working on that website as a speaker in those series in the past. You can see a large number of tools, and I only want to focus on the left column. I don't care about the color coded. That was something else that they were doing. But you see things like, okay, PD discretization, distributed parallelism, UQ, surrogate modeling, sparse linear algebra. And so to me, scientific machine learning really encompasses all of this, in addition to things that maybe people would say come first, like neural network or neural differential equations and those type of things, or sparsity detection and sparse differentiation. But all of this, to me, are part of scientific machine learning. To me, scientific machine learning stands on the shoulders of giants. You know, we use numerical methods from numerical analysis. They're implemented on HPC computers. We curate and analyze tons of data when we have tons of data, and we need to bring domain-specific knowledge into what we're doing. So the to-dos: don't ever forget to include your domain-specific knowledge, respect physical bounds constraints, integrate your data, even if it's noisy and incomplete. And all of this will further enable you to do predictive science, where you can do design optimization and certain quantification. So when I said standing on the shoulders of giants, people are already bringing scientific machine learning and the notion of standing on the shoulders of giants in publication. So here's just one I've grabbed from the web. Here's another one I've grabbed from the web. So it's really exciting times, and we can bring all of our prior knowledge and knowledge of our peers before us and move forward. So really exciting. So what is my motivation here? This talk is completely unclassified. The project was unclassified, but we're looking at radiation effects, but of what? Of nuclear weapons. If you want to learn more, you can get this book for $9.99 apparently on Amazon.com. So imagine that you have a high an energy source somewhere in a given landscape, and this is just a location somewhere in Nevada near an Air Force base, and you want to know the radiation field throughout the domain. You may have to solve an expensive equation that I will discuss, and out of that solution, you will be interested in quantities of interest, and they're usually functional of the solution you're solving. And you can get those rates, radiation fluxes, and those can also contribute to further physics down the road, like will you generate EMPs and so on. Oftentimes the quantity of interest are very localized, so is the source, but everything happens in a very large domain. The sponsor of the project is an agency of DoD. It's DTRA, Defense Threat Reduction Agency. And And what they want to do, they want to assess the survivability of equipment and personnel in case you have a detonation. For this, you would need to solve the Boltzmann transport equation for neutrons, photons, and electrons. And unfortunately, the Boltzmann simulation engines are extremely expensive and may not meet the mission needs of DTRA. The scenario universe is also very large, much larger than what most nuclear engineers do every day. The computational domain can span several kilometers. You have a ground and sky shine effect. You have mostly low density material, but you have very localized high density material. And the region of interest are small, very small compared to the size of the entire domain. They have lots of sources of uncertainty. The altitude of the source, what type of spectrum, energy spectrum did the source have? Do you have humidity in the air? Can affect transport? What's the ground made of? And basically also what your region of interest looks like. So I think scientific machine learning can help with high consequence applications like this one, where we bring the best of everything we have, multi-physics, multi-scale simulation. We have a high dimensional input parameter space that can change the outcome of the application. In this case, we don't have a lot of data. We are actually working in a regime where I don't have a lot of data to verify this. But I want to have parametric simulations because I want to change some of the input parameters and see how the outcome is different. So I'll give you a brief overview of radiation transport, and then I'll move on to the other parts of the outline as we continue. So here we are solving a radiation transport equation. You may tell me, Jean, what is so complicated about this equation? If you, and I think you see the mouse moving maybe. It's not that complicated. You have an advection term, you have a reaction term, so a hyperbolic equation with a reaction term. No big deal. Talk to your math friends, they know how to do this. Well, the issue is that we have a redistribution of particles or energy according to the direction of light, and particles can change energy and can change direction. So that becomes a much more challenging problem. My phase space is not 3D, but it's 6D. I have 3D for the physical space, XYZ, but I also have energy and direction of flight of particles. So that makes a 6D space. The way we solve the Boltzmann equation shown above, and the material properties, the sigmas, this is a log scale. It severely depends on the particle energy as well, and the propensity of having an interaction can change by many orders of magnitude based on the particle incident energy. So we discretize in the energy, so we end up with a G-coupled equation. We then solve along the different direction. We pick a quadrature on the unit sphere, so you get even more equation, a coupled equation. And then for each of those equations, you still have to resolve space, for which we sweep through the mesh. So it gives you an order of an idea of how many equations we're actually solving here. I've done some numbers for you. If you just put a moderate number of cells, 100 times 100 times 100, a moderate number of directions, 1,000, a moderate number of groups, energy groups, another 100. And then, if you have discontinuous finite element, you can add about another order of magnitude of degrees of freedom per spatial cell. It's really not uncommon to end up in a trillion number of unknowns. Even though my equation is linear and we can all think of it as AX equal B, I can never form A. I don't have A. And actually the number of unknowns I have per vertex of my mesh is gigantic, more than 10,000 unknown at every single vertex. So A is never available. The type of problem we do, this is funny a little bit, I hope, but it rivals with the debt, the national debt of the US. So we keeping up. I think the US is at $27 trillion of debt, and I think we are at 23 trillion unknowns in our in the biggest simulation. So as I've said, we have expensive calculations. So here's an example where we have already close to 200 million unknowns, and we haven't even discretized in energy. Here's another urban environment simulation. This one it gets there. It's okay in terms of spatial resolution. Could be a little bit better in the other variables, but it's already 160 billion unknowns. Those are the type of simulation. And every time you want to change something, placement of a building, spectrum of the source, you have to repeat this. Spectral effects are important. This is a burst of 14 MeV fusion neutron at 14 MeV neutrons at 100 meters from a source. But as you move further away from the source, now we are here at the bottom, we are at 1 kilometer away from the source, the peak of the 14 MeV neutrons has basically vanished. They've been attenuated or they've scattered down to other energies. So we have to resolve a lot of things in our simulation. As a function of altitude, material properties can vary a whole lot. 10 orders of magnitude of interactions coefficient as a function of altitude. Here I'm showing this for 80 kilometers. And depending on where you put your source, either 20 kilometers in altitude or 60 kilometers, you can have quite different simulation. So we have a code that does those high order fidelity simulation. We've run it on massively parallel computers, but it's extremely expensive. So we've done some simulation on 1.6 million processes, very expensive. And those full order models that depend on parameters that you may want to change. So it's going to be very expensive to repeat the models if the sponsor wants to change the scenario they're looking at. We're not talking about doing a hero calculation once for all. We're talking about the sponsor has multi-query problems and they want the answer several times, many times, and quickly. So basically, they want to do a perturbation on or propagation of uncertainties or completely design a new experiment. So as I've told you, we have a very expensive simulation engine, and it does not meet the need of the sponsor to solve their problems this way. So they want fast and accurate surrogate model. So moving on, I'll tell you a little bit about reduced order modeling, and hopefully I'll conclude on the pins aspect. So, but first, a reduced order model for transport. The way you can think of doing a reduced order model, it's a data-driven subspace discovery. Usually you have a physical system, you have data that goes, parameters that goes into your physical system, you do some modeling. If you have you write a code, you have an expensive, you have a big system of equation and you solve it on your supercomputer. In reduced order modeling, we actually learn from a few high fidelity simulation, and we extract the essence, the dominant mode of our solution. A little bit like when you look at a picture and you see all the different columns in your picture, you can extract the dominant mode of the pictures. And you don't need as many columns as the picture has to have a representation of what the picture was. So here the picture had 1,600 columns, but with 20 column basis function that you discover through SVD, you have a good idea of what the picture is. We do the same thing for simulation. We find our mode that will be relevant through SVD decomposition. And then the only thing we need to do is linearly combine our dominant modes to find the new solution of the problem. So that can be quite fast. It's so fast that we write GUIs to do this, and the GUIs, they run in almost real time. So those are a screenshot of GUIs. Maybe in the essence of time, I will skip some of the aspect of how we obtain those expansion coefficients. They are projection-based technique. Some of them can be quite costly in terms of human investment in modifying the code. And I won't go into the details of this because I want to talk about pins a little bit. but you can get a factor 1,000 to 10,000 acceleration with those type of techniques. Because of the intrusiveness of those techniques, we decided to use machine learning to learn the expansion coefficient as well, and we use Gaussian processes to do this with quite good success. I can and the application is truly black box. I can show you just a couple of simulation. The data on the right, 30 minutes, 16 core, the full order simulation, the reduced order model, 5 milliseconds on the laptop, and the predictive error is what I'm showing you, because the ROM solution to the eye would be exactly identical to the FOM solution. So, but 5 milliseconds not on an inexpensive laptop. We've done this for the sponsor on very, very large domain, kilometer-sized problems. I won't go into the details, but that was very interesting. 100 billion unknowns, 60 minutes on 320 processors. The reduced order model, 10 milliseconds. The student was complaining it took 5 seconds to write the solution to the disk, because getting the solution was 10 milliseconds and writing it to the disk was way too long to the student. Let me jump right away to pins. I'm just going to let you read the 1 through 4 bullets here. We've also used artificial neural network to learn, boosted random forest, symbolic regression, sparsity promoting least square. All of those techniques, you can put them into the bag of scientific machine learning, but let me go to pins. So what about pins? I told you I've done projection-based ROM on transport. I didn't tell you too much about what I've done on diffusion and correcting the diffusion process. It looks like I've thrown the kitchen sink at my problem, and it was working. But towards the end of the project, maybe a year and a half ago, I started to hear about physics-informed neural network. Completely different solution technique, and Ulysses described it at the beginning of the seminar, so I won't go into the detail of this, and other speakers before me have gone through this. But I just want to mention that for transport, I don't have a 2-dimensional input layer. I may have up to 7-dimensional input in neuron in my input layer. I have all the position, I have the energy, I have my 2 angles for my radiation, polar and azimuthal, and maybe if you have time dependent, you have the 7-dimension. There's still a lot to learn and cover in using pins. For example, in highly heterogeneous problem like I have in my application, I've noticed, and others have noticed in other applications as well, that pins, the neural network tends to learn the more diffusive solution, and I don't want this, so because it's not physically the answer you want. So we've added Fourier features on the input stream, similarly to the work of Peridarkis. This is very preliminary results of using pins, about 3 weeks of testing at the end of August. But now Levi, get ready, because I have this, my semester is ramping down, so I'll have time to start bugging you, Levi. So on the left, you have the standard spatial discretization technique, and on the right, you have with very sharp gradients like this that a regular pins without Fourier features was not able to resolve. We were able to resolve very well those sharp discontinuities in material properties. So to summarize, I do a lot of reduced order modeling. I'm getting excited to work in pins and with you guys and more if anybody wants to join. If you want to know a little bit of what I do a lot of radiation transport, multi-physics, software development, and data science and machine learning. So I apologize, Ulysses, I may have gone a little bit overboard, but thank you. And if anybody has questions, I'll be happy to answer them.
Thank you, Jean. This was very informative. I like your extended or expanded perspective on scientific machine learning. And I had not visited that site for a while, but yeah, so Chris Ragusa, the guy behind that site, He gave us a talk here, right? And
yes,
so
that's who I was thinking of. Yes,
exactly. And he is very creative. Yeah. So we should look at his website for more. And definitely, but he's a Julia guy, so
I know. I think the
mean,
color coding red to green was whether it was usable or already existing in Julia or not. So that's why I didn't want to talk about the color in the middle of his graph, only what he was considering as essential tools for scientific machine learning.
That's right. So are there any questions from the audience?
I went a little overboard, but
no,
technically
that
we still
was
have
great.
3
No,
minutes.
you didn't go.
We still have 3 minutes, maybe.
It was fine. Yes. So any questions?
Yes, I have one.
Yeah.
Okay. Hey, Jean, how are you?
I'm fine.
This is Eduardo speaking. Yes, good. Good talk. Appreciate that. I have a quick question, not in pins, but in model reduction, as you might expect, right? So,
yes.
You mentioned that your system is linear.
It is.
So why is it intrusive? Let's say if you look at POD, why? I mean, can you not project the matrices offline and
Yeah, we've actually done this. So what you want to do is see the one slide I skipped here. So
okay.
So having the matrix of the full order model, you need to sandwich it by the bases of your POD left and right, because our system is so large, we don't store the matrix A.
Okay, I see.
So you would have a call to the full order operation just to do the sandwiching operation, and that's expensive. The gains that we get are not dramatic. Okay, and the other is because our operator is also linear in the parameters. You can view, for example, our operator has been, affine in my example is in 2 parameters. So the A1 and A2 are parameter independent, big matrices, but we can reduce them on the fly once for all.
Okay.
Because they're parameter independent, and then you can combine the reduced operator once you know the new realization of your parameter very quickly. But this operation, extracting and doing the sandwiching on that big code is extremely intrusive. So we spent several months going into the code and modifying this, and it's absolutely not a black box approach. Sometimes you have a commercial code, you cannot go into the source code and do that operation. I agree that affine decomposition is the obvious thing to do, but when you don't have access to the matrix or you don't have access to the source code, it's a little bit more complicated.
Okay, I understand that. Okay, well, yeah, I think I didn't. Now I'm reading your slide. It makes more sense.
Yeah, I don't have A. A is 200 billion unknowns. I'm not storing this.
Okay. All right, very good. Thanks.
That was a very good question. It's usually the slide you skip, okay? Any other questions? Any other questions from the audience?
I have another one.
Yeah, go ahead.
So a philosophical question that we always ask in reservoir simulation, which somewhat resembles what you're doing. It is if we should replace the entire framework with a proxy or parts of your machinery, right? So do you have a feeling for if going all the way to replace your entire simulation model, it is the way to go, or just looking at particular things inside that I know? I'll give you an example. If you have a multi-phase flow, you may replace parts of the multi-phase calculation using a proxy, like a flash calculation, the equilibrium thermodynamic state, right? So you just replace that particular component, and of course the system is much easier to solve, right? Do you have a sense which way to go?
Yes, but it could still be problem dependent. Or where's my equation? must be way before. The redistribution in energy and angle term is what makes the coupling between all those equations and requires resolution. And sometimes to have a good representation of this term, you need quite a high expansion. So replacing that operator with a machine learned operator, that's already beneficial, and you keep the rest of the framework the way it is. Mm-hmm. Deciding on the energy structure is also something that is a little bit of a black art, and having a process from machine learning that determines, do I need 100 energy groups, or can I find the boundaries of the group in a more so that the physics is preserved, but in putting the bounds in a smart manner, so I only have 10 groups instead of 100 groups. Optimizing the group boundaries, this is also something that people are looking at. So you don't need to wipe out everything from what you do. As you said, you can actually try to use scientific machine learning to help improve pieces, and you keep your general framework. Sure. I know that going all the way to pins is wiping out completely what you've done, and replacing it. I'm still interested in that part nonetheless.
Okay. Fair enough.
You need a very expensive supercomputer for solving those equations. And nowadays, those supercomputers, they get more and more accelerators and GPU on them.
Yeah.
So, at some point, there will be supercomputers, or there already are supercomputers with a lot of GPU nodes.
But you got to keep in mind that the problems get more complicated, right?
I think
yeah.
That's why, and another thing with the way all the variable in the phase space are coupled, you cannot just do better in space or in energy, and then you will see starting your discretization error will show up. It's like a whack-a-mole game. If you want to do better, you have to almost do better at every single variable, and that's a pain.
Right. Okay. Very good. Thanks.